Hello YouTube, De-bodgery here, aka Richard Gumfaw on Facebook. Welcome to EV Components Review. In front of you today is the Tronic 750 control board. So this is everything. This is all of your low voltage electronics, this is all your high voltage components, all your power electronics, all in a single board. This is in a lot of ways very similar to what Benjamin Vetter does with the Trampa controllers, all very integrated, multi-layer boards, everything all on one board. There's a lot of similarities between this and what he does, with the exception that he does not do anything over 100 volts, whereas this is a 150 volt max controller. Of course, all of that went inside this nice, gorgeous box, which I just absolutely love. I think these are just absolutely gorgeous, and when they start doing them in colors, it'll only be prettier. Anyway, yeah, super pretty. The battery minus and battery plus wires, they solder down to one of these. So this is a QS10S connector. So they're anti-spark, and they are quite beefy and expensive. You can go find these like on Amazon or eBay or AliExpress and go look them up. I think I found them for like $45 a piece. Yeah, not cheap. Yeah, really. But that's the Tronic way. They don't skimp on anything. They just use the really good stuff for everything. Yeah, and that's definitely the really good stuff. Yeah, even things like on here, their connectors. These are all Molex. So yeah, everything else out there in the VESC world and a lot of other stuff is, this kind of stuff. This is JST 2.0, which works fine. No problem with it. But yeah, Molex is significantly more cost. All the components here are all Western components. Nichicon capacitors, Infineon MOSFETs. Yeah, everything here is all the best parts that they can get. Tronic doesn't skimp on anything, and if they do find something that they think is subpar, well, they replace it and they do something better. Yeah, they don't they don't skimp on quality anywhere that they can possibly avoid it. If they find something, they change it. So yeah, that's something that has made their production happen slower than other folks, because if they find something they don't like, they just don't sell that thing. They just do it again until they figure out whatever is going to be the best place to do something, best way to do something. And so, like in the time frame that I have gotten this repair board, I know for a fact that they have already made several changes above and beyond this, because I pointed out some stuff that they now want to change, and some of that stuff was easy to implement. Like putting a little bit of silicone on these high side DC to DC converters, or the way these capacitors are stuck down. Do a little bit of change in there just to make it a little bit prettier, a little bit nicer. So on and so forth. So, little fiddly changes like that they can do right away, and other stuff that takes a little bit more effort, that will come along over time. So anyway, let's talk about what we have here. Alright, so first thing I want to point out is anybody who's seen a picture of this thing, of which there are those out there on the internet, there are these three bridges, and they go across right here, and then the phase wires are soldered down to them, across this whole entire surface. So this is a repair board, so I can have those off so we can see underneath them. So this was good, and I just need to make sure you all know that that's what this is. And there's no MOSFETs populated on it. These little bridges right here, this is a heavy little piece of circuit board. It's because there's not much circuit board here. You can see in there, that's a lot of little tiny vias in there. I didn't count them. I'm not going to. But yeah, this is basically a whole bunch of copper held in place by a little bit of circuit board, because yeah, I would say that this is probably, I don't know, 60% copper right here. Not much circuit board left, because there is a million little vias inside those things. And then with that phase bus, or the phase wire being soldered down right there, this makes for a pretty stout phase bus that, well, it's going to hold up just fine. Maybe, I don't know if this will happen in the future, but these might go away, and instead there would be like a little copper bar that would be right here at the MOSFETs and over here, and this would screw down to it, and that would change that a little bit. But I don't know if that's going to happen. That's something that got talked about, but we'll see. I know this much: if the guys at Tronic don't like something, or they find a better way to do something, they change it. And yeah, Anyway, right here, this is your battery plus bus, and here's your battery minus bus, and as you can see, it's a copper bar there that's soldered down. So very good there. There is a very, very, very good current bus here. So here's battery plus. Your MOSFETs are within 1/8 of an inch away. They have circuit traces on top, and this is a multi-layer board, and there's circuit traces inside as well. So yeah, as far as getting current from the buses to the MOSFETs, that's pretty good, and it's an exceedingly short path anyway. But the only way to make this better is to use a very completely different design and essentially copy what Benjamin Vetter did, which is probably the best current buses for the least amount of torture and longest path or shortest paths possible that I have ever found anywhere. But this is still really, really good. You know, if Benjamin Vetter's a 10, I would say this is like a 9.75 or a 9.5 or something like that. Still really good. And I'd also have to put like the EBMX X9000 up there too, you know, like a 9.5, 9.75, which is also very, very good. So yeah, your copper bus is right here. You've got ceramic filtering caps at each one of the phase buses right where it should be. So best case noise suppression for high frequency noise, and also, being that you have such a really good bus here, you don't need a lot of low-frequency filtering, aka electrolytic capacitors. And talking to the engineer about this, he goes, you know, I've checked this over and over again. My capacitors don't get hot, and this is a classic sign that your large capacitors are working hard as they get hot. And he goes, they stay at ambient room temperature. They don't warm up. He goes, and then when I put an oscilloscope across my bus to look at noise, you know, under like maximum power, he goes, it's really quiet. There's very little noise on there. He says, I don't need more electrolytics. So, you know, on most controllers, I'm used to seeing a lot of electrolytic capacitors, but you know, the electro engineer, he says, you know, it's a super quiet DC bus. I don't need more, and they don't warm up, so they're not working hard. Anyway, all I can say is, yeah, okay, that's the proof I need. You know, whenever I replace capacitors, I always use bigger ones than what were there, because usually when they blow, the electrolytics, you know, the top pops open, they bulge, all that kind of stuff, because they got hot from having to work hard. And so I'll put bigger ones in there so that they work less hard. And, you know, these are sufficient for the job. So the fact that there's not more, this isn't worrisome once you understand why they're not there, because you don't need more. Okay, so here is your battery minus bus, and these are high current shunts, and this is the battery minus or low side current sensing iteration of VESC. Trampa uses that. FlipSky uses that. Yeah, there's a half dozen other VESC. Schul uses low side current sensing. So it's a very common method. EBMX, they do it right off of the phase wires instead, which is the other iteration of VESC. Either one is acceptable. So yeah, this is a very, very good way to do current sensing. Now that I understand what it's about. But yeah, these two shunts right here, they have a bunch of vias around them. This pad where it solders down is just an absolute sea of little tiny vias in there. So lots of good current path from here to here through the shunts, and also inside the solder pads and things. And then the distance from here to the MOSFET legs is very short. And then there's a large piece of copper here on the top and also on the bottom for getting that current to the MOSFET leg. So, and that's true for the battery plus side as well. There's plenty of copper here, despite that little gap, for making that be a pretty tight current path right there without there being any problems. And this is a multi-layer board, so you have traces inside the board and on the surfaces, top and bottom, which is part of the reason why you can make such a compact board. And it's also why it is like the Trampa stuff is also very compact. It's because you have the ability to put circuits on both sides, inside, you know, pretty much everywhere. Whereas, you know, like with stuff where you have a metal backboard, you know, PCB stuff like you see in, say, like KO Moto or Schul or EBMX, those ones, you know, the power stage, it can only be on the surface, and you can't have circuitry inside like you can here. So it's a different design goal. You have different benefits and disadvantages, of which this one has, because you can get all that extra circuitry really close together, is compactness. So that's one of the advantages of this design. Anyway, this stuff here from like here up, that's all your high voltage side, so that would be 150 volt max. And everything from here down, that's all your battery minus side. So the most you're ever going to see there would be like, say, 12, 15 volts at most. And most of the time, not even that, because it is the battery minus side. So everything from here down is doesn't need electrical isolation. It does have it, but it doesn't need it. And everything from here up does have it. So these are isolated DC to DC converters for providing power to like the gate drivers and the other small electronics that are here. And these gate driver chips are also isolated themselves internally. So everything here on the high side is all electrically isolated. And on the low side it is as well, just not quite as much, and it doesn't need it anyway. Same MOSFET drivers. These are all electrically isolated, and you have a little DC to DC, which I believe powers these three little current filters, or shunt, what do you call those, phase filters. So this is a full VESC implementation. You have a Bluetooth module here, which is inside the metal box, which I found interesting, but it has an antenna connector, and they include, or I think they're going to include, the actual antenna that you can plug in there if you want to use it. But it will work through the metal case, which I found astonishing. So it's got to be delivering some significant amount of power to be able to pull that off. This isn't your typical low-power Bluetooth modules, how that's got to be. Here's your DC to DC circuitry. So there's the big one that provides 12 volts, and then this one here does 5 volts, and then you've got 1117 linear regulator producing 3.3 volts for the STM32F405 CPU. Right here, this is a programming port. Most of the time, firmware, things like that, is done over USB, over Bluetooth, and that usually goes just fine. But there is a chance that you could potentially, during a firmware update, brick the CPU. And they have included a connector on there for that, so you can plug in an ST-Link and reprogram the STM32F405. Whereas with most VESC stuff, you don't have that. On some things, like say the EBMX X9000, they have a 4-pin set of holes that you can put your programmer into to program. And I've run across that on something else, and I forget what it was. But like none of the Trampa stuff has that. None of the Flip Sky stuff has that. I don't think Schul does. They don't even have the connector. They don't have anything for programming the STM32. It's either done by USB or Bluetooth, and that's it. So this is another over-the-top thing. You know, all of these are Molex connectors, which are very good. You know, they're not cheap. All that stuff is great. This is a USB-C programming port. So good attention to detail. Can't really fault anything here. Very nice, tight current paths. That's all pretty good. Can't really get a whole lot better than this. You can get a little bit better, but not much. These are pretty good. These are pretty darn good. And even this is, you know, it's an interesting layout, but again, that's not a tortured current path. It's literally the shortest distance between the high side and low side MOSFETs that you can get with this design of having your power buses right in the middle where they can do the most good. So yeah, that's kind of a clever idea to put the phase bus right on top of it, but yeah, it's not necessarily bad either. Alright, other side of the board. Not much to see here, but about all I can really say is you get a whole bunch of vias, so battery minus and battery plus. Yeah, this is just a little sea of vias in here for both of those. Here is one side of those shunts, and that's again just a million little vias, and those have vias on them. There's plenty of copper here inside and on the bottom and the top of the board. In fact, this whole entire center section here, this is all a big plane of copper that's all battery minus. There's plenty here, both inside, on top, and the bottom of the board, on top of the copper bars that are there for conducting current. I can't really say that's bad. These are not the MOSFETs, but they are representative. So these are the TO247 package MOSFET, and they go kind of like this and like that, and then the legs get really close together, about like that. So they kind of do this sort of a thing, come together pretty close. But the TO247 package has got a lot of benefits because it is such a large package. So as far as transferring heat away from itself, it does that really well. The legs themselves on it, so the fat part of the legs, are rated for 150 amps. As far as current carrying in this package, it's pretty good. Can't really fault any of that. So yeah, having those MOSFETs like this really close together, and then this gets sandwiched down right to the underside of that heatsink, yeah, it's going to do pretty darn well. Can't really fault that. I guess about the only thing you could do better, which would use real estate a little bit better, but the current capabilities aren't quite as high, is the D-Pack 2 package. So you basically get like 2 MOSFETs in the same space as you do one TO247, and you know, with those 2 MOSFETs, you'd probably get the same current carrying capability through the package as you get with a single TO247. So that would be like a little bit different or something like that. And I've talked to the electrical engineer that's done this development work, and also the owner, about something like that. And it's like, yeah, maybe later. Right now we just want to sell these ones because they're already really good as they are. So anyway, yeah, that's kind of how those MOSFETs go. And again, the current paths are really, really, really short. So yeah, that's all very good. When you're looking at it from this side, it makes sense why these copper bars are where they are. Because you can see the legs right there. You can see where the through holes are for the legs. And then the MOSFETs are right there. So yeah, very, very short, not tortured current paths. That's pretty darn good. Right here is a 7815 linear regulator. I believe that little linear regulator powers all of these guys. Anyway, that's pretty much everything that's here. It's a pretty straightforward design. Not much to do here that would make it better. Yeah, other than like redesigning it with some completely different designs or something. So can't really complain about this very much. This is a pretty optimal design.